Good morning. Welcome to Krishna's Verse. Let us take up the problem that we were after reading, the completeness of LP spaces. Now, the objective for embarking on such a long journey from Riemann integration to developing the whole concept of measure integration and so on was prompted by the incompleteness of RAB, where AB is a compact interval. So we were looking at this one. All Riemann integrable functions on the interval AB, and on which a norm was defined. I'm not going through that. And then we, to our disappointment, it was found that this is a normally linear space which is not complete. Not complete in the sense that Cauchy sequences of Riemann integrable functions may not converge in the space, or at least there exist some Cauchy sequences in RAB which is not converging in RAB itself. Now, this is a dreadful problem as far as the analysts are concerned. So, they'll be often playing around with sequences and sequences which are likely to converge, and then, if so, which we have designated by the so-called Cauchy sequences, and which we would like to converge in the same space, so that playing analysis on such spaces is a safe activity. I often give this example. Think of having a football game on the deck of a ship where the deck is not having a wall. Now, what could happen? We chase a ball, and in all your enthusiasm, there is nothing to stop the ball, so you may end up in the sea. Now, the non-completeness problem is something like this, because we may be chasing a worthwhile sequence which ultimately may not converge in the space, as you have seen in the case of RAB, where it doesn't. There are sequences which are convergible, or what you call Cauchy, but do not converge in the space, so RAB is not complete. And this is one of the problems that prompted that we do not have sufficiently large functions to make a similar space complete. And that was the problem that prompted, in a big way, our exercise going from Riemann integral to Lebesgue integral. And this was not an easy task, because we had to devise whole lot of new machineries, like the concept of a measure, that is generalizing the concept of length, but in the bargain gaining a lot, and then talking about functions on such spaces, and so on. And it was a beautiful. The experience that you have gained by working on RAB turns out to be very useful in this regard, but that comes to a fruition with the with the observation that the so-called LP spaces on measurable sets is a complete metric space. In fact, it's a complete normed linear space. So LP is complete. That means they are all Banach spaces. Okay, so at least an analyst need not be very much worried while playing analysis on this particular space. That is the whole objective. Now let us recall. I have done this in elaborate detail, and even eventually proving the so-called Rees-Fisher theorem. And we are not going to prove any one of them, but certainly we would recall the language that we need to communicate here. Okay, so let me start now. Let E be a measurable substitute. In fact, there itself we are going for a further generalization from intervals, bounded intervals AB to any measurable subset of R. So in a more general setting we are working now. Let script F denote the set of all F from E to R star. R star is extended real line, that is extended real valued functions. With the property that F is finite almost everywhere on that means except on a set of measure 0 on a subset of E of measure 0, the function is takes finite value, takes values in R. This is the mean. Now on this collection, see this collection turns out to be a linear space. On this collection, we define a relation F is, and this turns out to be an equivalence relation. F is related to G if and only if Fx equal to Gx for almost all x. That is the set on which it fails to happen as measure 0. That means the measure of the set equal to 0. That is the meaning. That means it is almost everywhere. The functions f and g are the set on which they differ is a set of measure 0. Now you can show that this relation is an equivalence relation. An equivalence relation on F. On script. That is reflexive That means F is related to itself. Symmetric. That is, F is related to G, implies G is related to G is related to F. And finally, transitive. Which means F is related to G, G is related to H, implies F is related to H. Okay. Now we introduce this notation. Let bracket F denote all G belonging to F script F such that G is now for each F, you can say F belongs to so let F tilde be the collection of all equivalence classes. Now we have seen that this is an equivalence relation, therefore it partitions F into equivalence classes, and let this new collection of equivalence classes be designated by F tilde, which is the collection of all blocks F where F belongs. So this is what you have. Suppose this is your F, then you have the equivalence relation actually partitions this into. So this is okay. So this new collection is what you designate by F tilde. Okay. So on F tilde defines to define by equivalent, the class equivalent to plus and alpha F defined by this is scalar multiplication defined as the class equivalent to alpha. Alpha belongs to now to see that this is well defined. Why do we want to say this is well defined? And I am just repeating on several occasions we have done it. Suppose there is an F1 belonging to F and G1 belonging to G. See, if F1 belongs to G1 belongs to G, then F plus G, the block F plus G and this is true, and so also alpha is equal to alpha. This is what you mean by the vector space operations are well defined. So what you have is this F tilde to define this linear space. Now this is the construction of okay. Now we are in a position to define the LP spaces. So let us define LP spaces. So we do this in two cases, that is LPE for 1 less than or equal to P less than infinity and L infinity. Okay. So let us first start with this. So let us take 1. Okay. For that, we define for each P, you have a space. Equivalence class or the class equivalent to the F with the property that integral over finite. So these are, so we will be working on what are called, I mean these functions are all measurable functions, and you see that this may be infinity or this may be finite. So we take only the subcollection for which this is. Then this is true for, I mean you do it for each element. Now let me see what do I get out of. Now LPE that we have defined is by definition a subspace of F. That's how we have picked up. Infinity all subspaces of so they're all linear spaces in their own right. Okay, with the addition and multiplication that we have defined. Now we also observe that if Fg belongs to F, then we have mod g. In fact, this is a if and only if. For classes of functions, I would strengthen this. This property is satisfied. Therefore, it is immaterial what function we pick from the class to compute the integral of the pth power. Okay? So that's it. So we define. So this is what we have for LP, and then we define now L infinity. We want to consider L infinity. So for that we define the concept of what is called essential bonds. We define F belonging to essentially bounded on provided there exists some m, some real number m, positive or non-negative, which is called the essential bound called the essential bound of F such that provided there exists some m greater than or equal to 0 such that less than or equal to m this is the condition. Okay, that means except possibly on a set of measures 0, it is not bounded. Okay, give some flexibility on that. Right? Now, like LP, L infinity E is also a real space. Now, we'll put it in one statement. Okay. He said for now that's a linear subspace of it. Okay. So we observe that it is much more. It is a normed linear space. Linear space. It's a normed linear space. So LP is a normed linear. Okay. So we shall define for that. We shall define norms. Okay. For P, okay, define the P. Sn infinity and for P equal to infinity, essential supremum F over P, the essential supremum of F taken over. So these are the equations. Now what one can show is that each of them, one can show that on the respective spaces LP. That is, what we can prove is the following. That means we are providing the space more structure. Okay. So let me designate at this stage for convenience. Let us Yes. Means we are now working in F tilde with this whole block uh, designated by. Okay. Now that means that is henceforth designated by. So wherever you see this, you have to read this whole lot of equivalence classes, etc. Okay. Now you know that. Okay. Therefore, what you can prove is this norm of f is equal to 0 almost, which means this is equivalent to the 0 function. That is f is equivalent to 0 function. That is the rule. Of course, what we have is this. Further, you have norm of f plus g. This is the triangular inequality. And further, you have so these properties are such. Okay. So we have these properties ensure that your space is this. So you have f g belongs to np mu and alpha belongs to. So it's a norm. It satisfies all the requirements of a norm. That means the space is now endowed with a concept of length for each vector. Okay. What further consequences? Then this length function allows you to define a distance. Okay. Now we define what is called the distance. Induces a distance on defined by and you can easily show that this is a distance function. So dp defines a distance from r with the properties almost where that means f is equal to g in the equivalence classes is to produce the same equivalence classes. Further, you have dp of f, and you have the triangular inequality So these inequalities are true. That means it becomes a metric space. And hence a topological space because it's a set of objects. So you can now comfortably talk about convergences. Okay, so the structure is now complete for that. Right. So it's a metric space. Now the question that you ask is this. Okay, let me define what is a convergent sequence or a Cauchy sequence. Definition. Converges to F belonging space is said to converge if given epsilon provided given epsilon positive, there exists and n depending on epsilon such that is convergence, usual convergence. Okay, and the point is that the sequences, all sequences may not be convergent. Okay, even if the sequence which may appear to go closer and closer as n becomes large, may not have a limit in space, as you have seen with the case of Cauchy sequences. Just recall the situation. The analogous situation is this. That is, you know that Q so Q is a metric space, it's a subspace of R. Okay, but there exists sequences in Q which do not, which may stay closer and closer as n tends to infinity, but may not converge to does not converge to an element. For instance, you take the exponential number. What is the rational sequence that creates it? 1, 1 plus 1, 1, 2, 1 plus or 2 plus 1 by 2 factorial, 2 plus 1 by 3 factorial, 2 plus 1 by 2 factorial plus 1 by 3 factorial, etc. So they are rational numbers. You know that gets closer and closer as n tends to infinity, but it does not converge to a element in R. In fact, it goes to the famous exponential number, which is at the cornerstone of mathematical analysis. A similar situation can arise here. Okay? So what you can have is that there are sequences which may not converge to F. May happen. I mean, you don't know actually. But on the other hand, if you are working in R, see that every sequence with the property that the terms get closer and closer and they appear to converge would certainly converge to an element in R itself. So that is what is called the completeness problem of R. Okay. So here also the similar situation arises. What does it mean? We take sequences which get closer and closer to R, but this is a vague terminology. So let us make this. So we define what is called a Cauchy sequence. A sequence Fn is said to be Cauchy said to be a Cauchy sequence if the following, what does it say? That is, the terms get closer and closer as n becomes large. That is roughly the. So we have to express it in a precise mathematical language. If provided given epsilon, there exists in n epsilon. To that everything goes like convergence, such that n epsilon. That means given n epsilon possible, you can find, or you take the epsilon neighborhood of f of okay. The terms would get closer and closer so that they all stay in some what you call set of radius epsilon, but still it may not converge to anything in general. I mean, we cannot assert that unless you prove it. For instance, we know that the rationals have this property that it is not all Cauchy sequences converge into space, whereas the real number system has the property all Cauchy sequences converge into space. And so you say R is complete and Q is not complete. So we have the analogous situation. So we shall say that LP is complete if every Cauchy sequence the terminal provided every Cauchy sequence in LCE has a limit now. This is the completeness law. That means all convergible, the Cauchy sequences I would like to designate by the name convergible sequences. I mean, they appear, they get closer and closer so that they do appear to be converging. All convergible sequences have a limit, and this is further justified by the general result that every metric space has a completion. So that I will come to that. So we have now our question is, this is the this is the central problem. Okay, we have discussed it in all details, so I don't want to repeat it, but we'll just quote the relevant theorem which tells that in fact LPE is complete. Okay, so we will state the central result which gives this, namely the Viswa theorem, the important results in mathematical analysis. The Viswa. This is the answer to the completeness question that we have raised. Let E be R and then LPE is a complete norm the beautiful structure that you have. Brackets called a balance. This concept goes with the name of the great mathematician Stephen Vellat. Okay, and in particular, when P equal to 2, you get the so-called L2 space, and the L2 space is an inner product space, and it goes by the name Hilbert space. Okay? So I will just make a remark of that towards the end, but in general, it's a Banach space. For each P, with the property that 1 less than or equal to P less than or equal. Further, there exists a subsequence of Fn which converges pointwise almost everywhere. Almost everywhere, this except possibly when I set a measure 0 on E, that is almost everywhere. There exists a subsequence. You cannot say the whole sequence converges to F almost everywhere. But what you can say is that there is some subsequence which you can extract out, which converges pointwise almost everywhere on it. Now this is the central result that you have, the so-called is Fisher here. Okay. Now some remarks on this is worthwhile before we conclude. So all Cauchy sequences in this LPE are complete. And this was the problem that we encountered while working with Riemann integral. Because they were defined on a far more restricted class of sets of R. You know that we mark the bounded is zero. Of R. Then we have the so-called Riemann integral functions. Then of course you have the non-defined which is fine. This is fine, right? And this is of course essentially this one. There is again a similar thing as to get an equivalence class, etc. But I am not going into the details of that. It is very much similar to what we do. Yeah? Then consequently what you can say is that RAB is a normed Fourier space, and RAB is not. This we have done elaborate. In fact, for RABs this is actually with the same, the Riemann integral becomes, the Lebesgue integral becomes the Riemann integral. Therefore, the norm is the same. So this is what you have. This is a proper subset of this, and it's not complete. This is not complete, whereas this is complete. So L1 is the completion of you have all sorts of nice results that RAB is dense in L1. Okay, and the Riemann integral and the Lebesgue integral coincide for such functions. And you have the completion of this turns out to be array. In fact, you see, you have the general result which says that if you take any normed linear space, any normed linear space has a unique completion. That's a beautiful completion here, which is one of the comforting results that you have when you do analysis on such spaces. Okay. So earlier I said that all metric spaces have a completion. In fact, when they are normally linear spaces, they have a completion into normally linear spaces. So you get so there exists a Banach space which which is the completion of a given what you call normally linear space. There is a completion for every normally linear space. So in fact, here you have, they're all Banach spaces. And that's a very comforting, because you can do analysis, or you can stretch the analysis that you intend to do on that space to its completion. Very comfortable, with no difficulty. Okay. And that's the general abstract completion theorem. So another remark I want to make is you're talking about LP spaces. L2 is an inner product space. So L2E is an inner product. Which is complete, and therefore what do you get? Which is complete, and therefore call it every inner product space that is complete is called a space. These are all things that should be looked into more deeply. The structure of this. So the Hilbert space is a complete inner product space. So these are all very important spaces. So you have a whole class of spaces now available, which are complete. And the amazing thing is that it's not just L1 which turns out to be complete. Right? The entire class of LP is complete. Note that it is not the L1 space alone. In fact, every P This is ultimately achieved. And that shows the path we have traced out, starting from the Riemann integral, developing a new concept of integration theory, which coincides with the Riemann integral, wherever the function is Riemann integrable, but far more general than that, which gives you a complete normed Lego space. It gives you a Banach space. And that is one of the greatest achievements of this. Okay. So, in a way, we have now completed our journey of review from Riemann to. So, this is a review session. So, with 12 lectures, I have in a way reviewed. It became a bit lengthy, probably because of my insistence that should be made sufficiently clear. Okay. But the proof of all these things are quite sophisticated, and it is developed through a string of theorems. So one should go to the theory and see what happens. So that gives you a very nice platform to do analysis now. And it's for this reason that you see that it is not L1E that is complete, but LPE is complete for all P lying from 1. That is that one stroke we are not proving each one is complete. We are able to prove that the whole lot is complete with our machinery. And that's the greatness of the Lebesgue integration theory. Okay. So with this remark, let me conclude. And now it is time for me to introduce or generalize further and introduce the general integration. So thank you very much.